Hi, this is your tutorial for the continuation of special relativity. The focus of this little lesson is length contraction and relativistic momentum. Previously, we discussed how special relativity contradicts the concept of absolute time in Newtonian mechanics. That is, that measurements of time, intervals, are relative, and that they can be different for different observers based on their speed. More precisely, their speed as it compares to the universal speed limit, that is c. Time is just one aspect of a frame of reference, so we also have distance, measurements of distance and position, and that begets measurements of length. So it stands to reason that not only may there be time dilation or time stretching or squishing, but also length stretching and squishing, and this is length contraction. Consider the following example. We have an observer, we'll call him observer number 1, he's got a nice hairdo there, and then observer 2. And observer 1 is traveling on a train, might as well make it a train car, Einstein loved trains. And observer 1 is traveling at a constant velocity relative to observer 2, and he has in his hand a clock. Now, he's going to measure the length that we will call Ls here between points A and B by timing how long it takes him to travel that distance. He knows his speed. We know that speed is equal to distance over time. If we know our velocity and we know how long it takes for us, how long we're traveling for, we can measure our distance, or our Ls, by multiplying our velocity by our time. You'll remember, though, in relativistic discussions of time, that the time that passes for the moving frame of reference is equal to the proper time, or the time interval as it is experienced by observer 2, the stationary observer, divided by that Lorentz transformation, which is the following. How can we discuss length contraction in terms of our time dilation? Well, we can easily make this look like this, and we can create a substitution. So by doing that, we multiply both sides by our v, and now we have our v multiplied by our time is equal to Ls. So v delta Tm is equal to the length of distance traveled between points A and B. Remember, we're trying to compare how that length distance compares in the frame of reference of the orange-haired brother and the observer number 2. So we can also create an expression that says that v times delta Ts, the time that passes for the second observer, the stationary observer, is equal to L. And we're going to call that Lm to differentiate it from our Ls, because we want to compare those. By substituting these equations into the time dilation, we get Ls is equal to the length of the moving observer divided by the Lorentz transformation. And now we're interested in solving for Lm, that is the length as measured by observer 1 on the train. So we can rearrange this, and we have Lm is equal to Ls multiplied by the Lorentz transformation. And this is our formula for length contraction. Now, I'm not expecting you to use this formula. Of course you can, and I'll provide a couple of examples for you to play around with it. I won't be testing you on this because I think that the the formulas for time dilation demonstrate sufficiently your understanding of special relativity. Another way that you'll probably see this in the future is as a ratio of the length as measured by the stationary observer, the moving observer, divided by the length as measured by the stationary observer. And that's just equal to the Lorentz transformation here. What does this mean? Well, the result is that the faster a frame of reference is moving, the faster an object or frame of reference is moving, the shorter its length is as measured by a stationary observer. Think about what this means. And the direction of length contraction, the direction of contraction is only in the direction of travel. Okay, this is bizarre. This means the faster that you travel, your meter will actually be measured less than a meter as observed by an outside observer. And here's why. Let's say we have points, we'll call it F in G, and this object is moving this way, and this is 1 meter. And we have an observer here watching, and this thing is traveling at relativistic speeds, so close to the speed of light. As F passes the observer, G has moved just as fast in the direction of travel. So this guy is actually going to observe that this length stick, it maintains its thickness, but its length has actually contracted. It's been squished in the direction of travel. Pretty bizarre stuff, and has many implications for lots of subatomic research and particles that travel at relativistic speeds. We can have particles that are traveling really, really quickly, and some of their behaviors, if considered under Newtonian mechanics, are bizarre and actually don't agree with Newtonian modeling. However, once we apply the relativistic length contraction and time dilation to those objects, we see that everything is in agreement. So far we've investigated time dilation as a result of motion that is close to the speed of light, as well as length contraction. And some of the applications of these things are GPS satellites traveling at really high speeds relative to observers on the ground. Those GPS satellites must have computers that correct for time dilation so that they can speak to one another in correct time. Aircrafts that travel long distances and at high speeds, they also must have relativistic correction factors built into their computers so that they can communicate accurately with ground-based observations and air traffic controllers. So this stuff is all real and working in our everyday life, and helps to contribute to the accuracy of things like GPS and aircraft controller and a number of other applications that we see. Not only is there length contraction and time dilation, but there's also something called relativistic momentum. And I bring up relativistic momentum only because it leads to one of the most famous equations of Einstein's of all time. Momentum, we will learn later in the course, has a symbol p, and you find momentum by multiplying an object's mass to its velocity. You can probably understand that if momentum also is subject to relativity, that we can see p relativistic, the relativistic momentum is equal to mv as corrected by the Lorentz transformation. So I don't expect you to use that, but I bring it up only because suddenly we have not only length contraction happening, not only time dilation and momentum, but we also have mass being introduced. And this Einstein put into our concepts of the conservation of energy. And we know that there already is some description in Newtonian physics between energy of an object and its mass. So Einstein put our concept of equivalency of energy and mass together with the relativistic momentum, and he came up with the total energy is also subject to relativity. And he expressed that in this way. When the V moves to 0, when the mass is at rest, remember whatever that means, relative to the cosmic background radiation, relative to whatever frame of reference we're investigating, as V turns to 0, what happens? Let's keep our MC up here. So 1 minus 0 divided by the speed of light squared. 1 minus 0 is 1. Square root of 1 is 1. So when the object is at rest, Einstein said, its rest energy is equal to its mass times the speed of light squared, and that of course is E equals mc squared. We call this is the amount of energy an object has at rest with respect to an observer. And of course this equation opened up all of our atomic research, the development of the atomic bomb, saying that there's an equivalency between the amount of mass an object has when at rest and its energy. What's really fascinating is that as an object moves towards the speed of light, it actually has to lose mass in order to increase its speed. And so we consider things like photons. We say that photons have momentum through the relativistic momentum equation, but its mass must adjust to being 0 if the c is going to increase closer to 3.00 times 10 to the 8. Now the question is then, if an object has no mass, does it actually have momentum? Now, momentum is a weird animal, folks, and we will investigate momentum a little bit later. So what do you got to know here? All I would like you to know is that length contraction is a real effect of speeds that are relativistic, that are close to the speeds of c. That is, an object actually compresses in length in the direction of travel, and the faster it travels. This is a bizarre result, and you can imagine what a car would look like if it were zooming past you at relativistic speeds. It would actually look a bit squished, and that's pretty bizarre. For relativistic momentum, we'll get to momentum later on in the course, but I bring it up here not that you know it, but that you can see where E equals mc squared came from. Momentum is our way of introducing mass into relativistic math, together with our current understanding of conservation of energy, and the amount of energy that an object has is related to its mass and its velocity. And that leads us into E equals mc squared. So E equals mc squared is one of the formulas derived by Einstein to try to solve the problem of the speed of light being constant as observed in every inertial frame of reference, regardless of the frame of reference of the emission of light. And the second postulate is that the laws of physics are true in all inertial frames of references. All right, hope that went over okay. One of the most fascinating aspects about the course is modern physics, and we will dip into modern physics as we treat other Newtonian concepts.